Welcome back to another HVAC-Engineering-Techie video. You know, these training videos are educational in nature and are designed to help you in your career. Today's lesson is HVAC package unit basics. Now, you would assume that package units are dead simple compared to a chill water or hot water system. It turns out the opposite is actually true. Package units are more difficult, more complicated than a chill water or hot water system. And we're going to go through those things that make them more difficult. And we're going to talk about everything inside of a unit, what they do, and why it's important to know what's going on inside the unit before you tackle systems. So this video is the first one in package systems that describes all the components, and later on versions or videos are designed to tell you about the systems and how the package units fit into those systems. So before we go on to this lesson, I'd like to ask you to become a subscribing member if you would. It's free. It doesn't cause you any pain. It's absolutely simple. Just push the button down below that says subscribe. Give me a thumbs up if you like the video. And the reason for that is those items are used by Google to judge this video, which keeps me on the air. So I'd really appreciate it. Remember, the Techie channel is a channel that talks all things HVAC, from engineering design, construction, equipment, systems, test and balance, controls, efficiency and performance, and a few other things along the way. So let's get started on HVAC package unit basics. All right, so first we're going to talk about type of refrigerants. Refrigerants is in a changing mode right now, so we need to know a little bit about that. First of all, you can see this refrigerant chart. This has all the different refrigerants that we've used over the years. And there are changes. So refrigerant approvals are in flux due to ozone depletion capability. Now they call it climate warming, but basically it's the ozone depletion is why we originally did it. So CFCs, these two up here, which is R11 and R12, those haven't been manufactured since 1993. So they were banned in 1993. It's because the ozone hole was getting large. And then we went to HCFCs, which are these right here. And this is the R22, R500, and R502. And those were banned in 2024, which is this year. So they won't be manufactured next year. So we have replaced those basically with HFCs, which are 134A, 410A. And we're using those for the last 10 or 15 years. We've used these everywhere, but these are now being banned as of 2030. So in 2030, these are going to go away, and then we're going to produce HFCOs. And the reason is that each of these groups has a much less ozone depletion capability than one up ahead of it. So the HFOs, we're not quite sure which ones are going to use predominantly, but right so far we're looking at 454B. And 123YF and R32. Now there are others. There's a whole bunch of others out there they're looking at, but right now I think it's going to end up being one of these. Some people have already started going to 445B. You'll notice on the refrigerants that, like this R32, that's a pure refrigerant, but a lot of these are mixtures of like this. Like this one is 32 and 125. So there's a lot of different refrigerants because they're trying to get specific capabilities out of them. So future refrigerants are still being debated as a 424, I mean as 224 this year. So stay tuned to see what happens in the future. Now, when these get banned, we don't actually have to replace the refrigerant in them. We just can't buy new units with that refrigerant. So what happens is, as they replace the refrigerant, the industry stockpiles what they have, and as they remove old units, they take out the gas and clean it and refurbish it. And so they can still, so if you have an older unit, say you have an R22 unit, which is canceled way up here, you can still buy R22. It's going to get more pricey because this R11 and R12 are horrendous price. You know, they used to spend $35 for 35 pounds, dollar pound. Now it can be $600 or $700 for the 35 pounds. So this has gone up a lot. So this is a pressure enthalpy diagram, and this curve right here is what the refrigerant does. And this is basically every type of refrigerant has a different curve. And that's why we have different refrigerants. So what happens here is, as you look at it, the gas, which starts as a gas, and the compressor takes that gas and compresses it, which heats it up and turns it into a saturated vapor. Then it goes through the condensing coil, which turns it into a liquid. And then it goes back through an expansion device, which turns it into a saturated vapor again. And it goes through the evaporator and becomes a vapor again, a pure vapor. And then the compressor starts over, and that's the cycle. And that's how refrigerant works. Now, as a technician, you should keep a chart on your phone nowadays that lists what the different pressures and temperatures are for that particular type of refrigerant, and that's how you use that to actually charge a system. So you need for whatever refrigerant you're needing. So as we go through this transition, you have to have new charts of what pressures and temperatures this gas will be. So in other words, if you're trying to gas a unit, it's 95 degrees outside, then one pressure represents the different places on the curve. But if you're trying to condense it at 54 degrees, completely different pressure. Well, every refrigerant has different pressures and temperatures, so you have to have a different chart. All right, so this is a basic air conditioning system, how it works. As you can see, we have a compressor that takes the vapor, compresses it up, makes it hot gas. The hot gas goes through the condenser, and the outside air cools it to a liquid. The liquid comes down and goes through the expansion valve, turning it back into a vapor. The cold, it makes it really cold, and so the cold vapor goes through this evaporator, cooling the air, and the air actually heats the gas back into a vapor. So basically, this is a basic operation of an air conditioner. The air conditioner may have a lot more components, may have receivers and solenoid valves, but basically, this is the refrigerant cycle. And I basically just already said all this stuff, so I won't repeat myself. Now, this is a basic heat pump and cooling mode, which is exactly the same as the air conditioner we just looked at. So basically, you have the vapor coming in the compressor, heats it up. The only thing different, we have this four-way valve. So this four-way valve basically switches the evaporator and condenser. They trade places, and they do that with this four-way valve. The hot gas goes to the condenser now, and this air heats the outside air up because it's cold outside, and it takes this back to a liquid. And the liquid, something here's different. So we have expansion valves. We have expansion valve here and here, but they have check valves so you can go around them. That's because we're switching the evaporator and condenser. So when this is in cooling mode, it just goes right through the check valve, doesn't go through the expansion valve, comes over here as a liquid, can't get through that check valve, so it goes through this expansion valve, and it goes through the evaporator just like a normal air conditioner. And back. So I did it again. So now this is one in heating. So basically the compressor takes and heats it up and adds heat to it, goes through the four-way valve, and now goes to the evaporator and to the evaporator for heating. So the hot gas, actually the cold air from the room heats up the air, and at the same time it lowers the temperature of the gas, of the vapor, and it goes back to liquid. This time it goes around this expansion device, goes over, hits this valve, goes through this expansion device to the outside air, and this is really, really cold. So the outside air is cold because it's wintertime, but it's warm to this gas, so it actually heats this gas up, cools the outside air even colder, and it goes back and does it all over again. So the only trick here is to making sure you have a big enough condenser and your gas properties are such that the outside air can actually do this. So this begs the question, how cold is it outside? You know, if it's 32 degrees outside, heat pumps are struggling a little bit. If it's 10 degrees below zero, they're not working at all. So what we do with that situation is we put auxiliary heat into the heat pump. So if it's really, really cold outside, it can add some heat into the space and thus make the unit work. So it has a strip heater. In my town, we don't need those because it never gets that cold. It may drop to 32 degrees, an hour in a year, but basically normally we don't have that temperature, so heat pumps work great. All right, there's different types of AC units, and I'm going to represent some different typical sizes. Now these are typical. There are obviously some unit manufacturers somewhere making a different size, but these are what the average are. So cooling only units, residential is 1.5 to 5 tons. Cooling commercial, 6 to 100 tons. Now if you want to add heat to these, you put a strip heater downstream of the duct. So they are cooling only units. Cooling with gas heat, you can get gas heat at 3 to 60 tons. Residential wise, commercial 7.5 to 100 tons. So basically you can get cooling with gas heaters. You can get big gas heaters if you need a big unit. Heat pump units, residentially 1.5 to 5 tons. Heat pump units, commercial 6 to 25 tons. Now up here on this cooling with gas heat, this is actually should be 5 tons. 60 tons, they're available to 60 tons, but this really should be 5 tons. Interior package units. Now these are self-contained units that have compressors in them. They use them internally. We use them to cool large spaces, or we use them to do specialty cooling like computer rooms and things. These you can get commercially 10 to 110 tons. DOAS, which is a dedicated outside air unit, you can get commercial 3 to 80 ton. AC unit types, again, split DX units, which are residential 1.5 to 5 tons. Cooling only. Commercial 6 to 120 tons. Heat pump units, residential 1.5 to 5 tons. Heat pump units 6 to 20 tons, and these are split systems again. And then we have water source heat pumps, which use water to condense them. And the horizontal units are normally 0.5 to 30 tons. Vertical 20 to 60 ton. Ductless split units, which are designed to just use one space, to cool one space, and these are normally heat pumps. And they're a heat pump unit, residential 1 to 5 tons. VRF systems, which are the same thing, except they have a lot of evaporators and one condensing units. Their heat pumps are 6 to 42 tons. Now we're going to talk about the components. What goes inside of a AC unit? And they make these with all kinds of different components, and some of them you can get customized. Most of them are not. Most of them come right out of a factory as a standard unit. So we're going to talk about fans. We're going to talk about different compressors. We'll talk about DX cooling coils, which are refrigerant cooling coils, electric heating coils, gas furnaces, reversing valves, filters, dampers, humidifiers, unit controls, and condensate drains. So let's first talk about fans first. Typical for a lot of package units is a forward curve fan, which has these small kind of little cupped fins. And as the unit rotates, it grabs the air and throws it off this direction. The wheels come in single or double. This is a double width, double inlet wheel, which is typical of a package unit. And they sit inside, these wheels sit inside this volute, and as it turns, it pushes the air out this entrance here. It's a standard low pressure fan called a forward curve fan. We have a backward incline fan, which is low to higher pressure fan. And most of the larger units are all backward incline because it delivers a little bit more at a higher pressure. And instead of little curly blades like the forward curve, it has these flat blades but are backward inclined. They lean back. And a lot of people, when they see these, they think they're running backwards because they think they should catch the air and throw it off this way like a forward curve, but they don't. They paddle push the air this way. And it's important to know that because these are normally three-phase motors, which you can change the leads and make them run either direction. But if they run backwards, pushing air this direction, they don't do very much air nor very high pressure. So they'll do maybe 15-20% of the airflow when running backwards. So this is also a double width, double inlet wheel. We have plug fans. And plug fans are, again, a backward inclined fan, but they don't have a volute like the other one. They just have this inner nozzle, this volute coming in here, a way for the air to get in, and then it pressurizes a space behind it. And this is like a fan array. So the reason these became popular because they're lower cost. You don't have to buy a big volute, and two, they're narrower. They're cheaper and they take up less space. So the unit overall is smaller. And you can build them in arrays. So you can have arrays up to 20 fans or so. And what happens is these basically all work and they bring in air, so they provide some redundancy. And the main key is that these have small space. If you needed, if you have 6 fans, 3 deep, 3 high, 2 deep, or 9 fans, 3 by 3. To use one fan to do that would take much larger space than this. Now these have some redundancy, so if you lose a fan, you lose only a portion. Now you would think in this one you'd only use a third, but if you have just 3 fans, you lose a third. But that only happens if you have isolation dampers on the inlet of the unit. So you have these dampers that if this unit fails close, then that would mean this would be a third. If you don't have the dampers, then you actually lose 2/3 because you lose the fan that's pressurizing the air. But since it's not running, it's letting air come back this direction. So it's actually 2 fans. Even though 2 are running, you lost 2. So if you want redundancy, you got to have dampers on. So compressors can have hermetically sealed reciprocating. They're small, 1 to 5 horsepower. Medium capacity, 7.5 to 20 horsepower. And basically these have piston compressors inside them and electric motors that are installed inside of a sealed container and are open to the refrigerant flow. So the refrigerant has oil in it, so it oils the compressor as it goes through the compressor and cools the motor as it goes through the motor. So these are hermetically sealed. Now, if something breaks inside here, you replace the whole compressor. They can rebuild these, but to do that, they have to grind open the weld, fix them, put them back, and re-weld it. So don't normally do that. And these are not as popular as they once were because there's another one that's taking their place, which we'll explain in a minute. So semi-hermetic reciprocating. So what happens here, this compressor is 2 to 50 horsepower and you have unloaders for staging. So what happens is we have one hermetically sealed unit here that has heads on it that are the piston heads for the refrigerant capacity, and the motor's inside the hermetically sealed one. So if this loses a motor, got to do the same thing, got to replace the compressor, and the refrigerant and oil both oil the compressor and cool the motor. So, but the one good thing about these is if you lose a valve plate, the heads are not in the hermetical seal, so you can actually valve it off and go ahead and replace a valve plate in it. So that makes these, if you have a valve problem now, in reciprocating compressors, the valves are the weak spot. So this is helpful. You can actually work on the heads without dumping the compressor. Here we have open reciprocating. We have that same reciprocating compressor, but we have an open motor. So the motor, on this one, you can change the motor without getting in the refrigerant circuit. Now, I forgot to mention, this can have unloaders. What they do is they put an unloader on a head, and basically it's like some modern cars that can deactivate a cylinder. Well, this does the same thing. It deactivates those cylinders so they don't pump refrigerant, thus reducing the capacity of the unit. Normally they're 1/3 capacity. Normally they have 3 banks of cylinders. You might have 2. If you have 2, they're 50% reduction. So this is a large compressor. It can go from 5 to 150 horsepower, and normally 1 horsepower per ton, normally. So basically that's a big unit. Then we have a hermetic screw. Now this is the same thing. Instead of a piston compressor, it's got a set of vane compressors in here, which actually rotate and create pressure by the space in between the 2 rotary halves. And this is motors inside this hermetically sealed. So again, the compressor is oiled by the oil in the refrigerant, and the motor is cooled by the refrigerant. So these are modulating. They're large capacity, 5 to 150 horsepower. And this slide valve moves back and forth, thus limiting the amount of refrigerant into the lobes of the screw, thus making it modulate. So this is a good thing. It modulates. The screw compressors are fairly large, can be large. The only problem is they're noisy at a high frequency noise. So normally when you use these, we have to put some sound material around them so neighbors don't complain about the loud noise of the screws. These are hermetic scrolls. This is what's taken the place of the small hermetic reciprocating I talked about. And these, instead of having a piston compressor in them, they have a scroll compressor. It has 2 scroll plates that rotate against each other. And what happens, the space in between the scroll gets smaller and smaller as it gets to the outlet, thus pressurizing the refrigerant. So these are small capacity, 1 to 10 horsepower. Again, they're hermetically sealed so that everything's oiled and cooled with refrigerant. And this is a modulating capacity compressor. It's called a digital scroll. And what it does, it has a scroll plate that's movable. So it has a circuit here that uses refrigerant pressure, and it can move that top plate. So if it needs less capacity, it just pops up the plate for a minute and it loses its capacity pressure. And it does this at a pulsating factor. So it uses pulse width modulation to control that up and down. And that gives digital scroll. Now, basically, these are kind of falling out of favor because you can just take a regular hermetic and put a VFD on it. Now, it's variable volume, which is much easier and much less trouble because these can't fail. Whereas a VFD, the scroll is just a normal scroll. So these have come up in the world as hermetic sealed. Now let's talk about DX coil, which is a refrigerant coil. And they come in 1 to 6 row, and they come 8 to 24 fins per inch, just like a cooling coil. However, just because you can doesn't mean you should. You should never have a 24 fin coil because they're very, very difficult to clean. So if you look here, this coil, this is the fins, and it has tubes running through this coil. And the refrigerant comes in here to the thermal expansion valve, and it has a distributor that distributes refrigerant to every single row. So as the refrigerant, it's got a little tube that goes up to that coil, and it goes through that coil, comes back here, goes in, comes back, and eventually comes back to the suction header, which is the return refrigerant to the compressor. And that's the way these work. The reason we don't like 24 fin is because these fins are so close, we can't clean it. Normally, I like to see these coils between 12 to 14 fin. You might get 16 fin, but after that, they start getting hard to clean. The reason they're hard to clean is because the way we clean it, we put an expanding foam detergent on this side, and as it works its way through the coil, we take water under low pressure, like a garden hose, and spray it on the coil so it doesn't damage the fins, and push that through the coil, thus cleaning the coil. You got 24 fins per inch, you can't get that stuff through the coil, and it'll impact the coil. And the coils need to be cleaned every once in a while because it drastically affects the capacity of the unit. Now, this is an A coil. Now, unfortunately, with package units, you probably don't have a choice to tell them what fins you want. They design it the way they want, and that's what they build, and that's what you get. Unfortunately, 24 fin is cheaper because it provides more heat transfer for less coil. And that's why the manufacturers do it. It's unfortunate because it makes the unit lose efficiency over time. This is an A coil for a furnace section or a vertical fan coil, which the header is down here, and it distributes the same to these coils. And the air comes up from the bottom and blows through these A coils. And the condensate drains down these into these small channels here and to the condensate drain. You can have multiple stages in a refrigerant system. You have normally what we have is a coil for each stage. So if you have 2 stages, you have 2 coils. And the only thing is this is called a phase control because they're on top of each other. And the only thing about this you need to understand is you need to always make sure this one is, if you only have 1 stage on, it needs to be the top one. If you make the bottom one the only one on, then this is a dry coil. This is a wet coil because it's drawing moisture out of the air. Then this coil has a lot less air friction than this one. So more than 50% of the air will go through this one. So you ended up with less cooling capacity. But if you make this one the one on, the condensate drains down, wetting both coils, making the same air pressure. So that's how you do that. Phase control, that's what this one is. We can have row control. We have 2 coils in series. And you say, well, why would you ever do that? Well, you might have where one is a pre-cool coil, one is a cooling coil, or you might have a coil that you need more capacity. And so you want 2 6-row coils in series because you need a big temperature drop. You can do that. Intertwined coil is where you have multi-stage and only 1 coil. So you have these 2 distributors, each with their own expansion valve coming in from that circuit. And what happens is this one goes to this one, and then the next one goes to the next one. So every other one is from a different circuit. So no matter what circuit's on, the coil is always cold. So it doesn't have that problem. So when we were first working on this, we talked to wonder what's the best coil. So we asked the different manufacturers, and we thought it was funny because they told us what they do, not what's best. To them, if they made intertwined coils, that was best. If they made stacked coils, that was best. And we figured that out later because intertwined is actually the best. It's also the most expensive. But I thought that was funny. Heating coils. Now, heating coils are hot water coils. We can heat with refrigerant coils. In a lot of supermarkets I've built, we used hot gas off the compressor, and we use that hot gas to heat air in the supermarkets. Because if you notice, when you're in those ice cream rows, it's cold. So what we do is take that air off of it and heat it up for the rest of the store. So you use hot gas to do that, which is efficiency. But you also can use hot water coils from a hot water system. Again, hot water come 1 to 6 row, 8 to 24 fin. Again, on a hot water coil, never use 24 fin. You can buy this anything you want, so buy it at 12 fin. Be better. Electric coils, electric heating coils. This is our stage coils, 1 to 8 stages, 1 to 5W coils, 5 kW coils. And you can get these with contactors, so they're single stage, they come on and off. Or you can get it with an SCR, which is a silicon control rectifier that actually modulates the voltage or the current. So basically they become modulating. So this is a standard electric coil, and you see it's got these exposed wires in it like your toaster. So they turn bright red when they're operating. And there's a couple of conditions with this. One is they need air across the whole coil. You can't have stratified flow across these coils. If you had a corner like this coil right here that didn't have much air, then this would get red hot and eventually would burn out right here because it doesn't have enough air. So in that condition, we put air baffles up to push more air towards the spot that doesn't have any air. These also have a clicks on here on the downstream side that watch the temperature. If this gets real hot, it turns it off because it knows it's going to be burnt out. The other little issue with these is we have a red hot coil. So if you put a piece of paper in the duct, you could catch it on fire. It will definitely smoke, may actually catch on fire. And if you have lint coming down here, it will generate smoke. So basically, we try not to use these type coils in anything airstream that has stuff in it. It needs to be clean air. So those, we have cowl rod heaters. And the cowl rod heater is the same. It has that exposed wire inside this tube. It's a steel tube. So basically, it's not quite as hot as the other, and it never gets hot enough to burn something. Still provides heat for the air because the air is cold. And it's the same thing. It has a clicks on. It's called a cowl rod heater. It's much more rugged, much more robust, and will survive where that open wire will not. Gas furnaces can have a heater inside your air conditioning unit, which is normally on the suction side. And basically it has this burner area down here where the hot gas is coming off it. It goes up these flues and goes up to the top where it's sucked out to become exhaust, the flue exhaust. And these heat the air. These hot flues heat the air. Now this can be single stage or multiple stage if it has more than one gas valve, or it can be modulating if it has a modulating gas valve. It's typical. Or you can get a unit with gas duct furnaces. Now these duct furnaces go on the discharge, on the supply duct, and they are supply duct mounted, and they can be single stage or multiple stage, and they can also be modulating. And the best thing about them is you can also put multiple units in series. So if you're doing a job somewhere that has really cold air and needs to be heated up, you can put 2 or 3 of these in series. And so you can, instead of 10-degree rise or 20-degree rise, you can get 60 or 70 or 80 degrees air. I've used that several times in the industrial where I needed, 150, 160, 180, 200-degree air, and I do that by putting a lot of these in series. Then you can have a gas furnace like you have in your house. These can be vertical, they can become horizontal, and basically they have a blower and a gas furnace, and the air goes out, the conditioned air goes out this way, and the flue goes out the other way. And you can put a cooling coil on top for those heating and cooling, of course. Okay, heat pump reversing valves. So all the heat pumps need that reversing valves to make them reverse the condenser and evaporator sections. They're 4-way valves. The only thing with these is they can be normally open or normally closed. And they're 4-way, so you have to tell what that is. And what that reason that matters, it needs to go to heating. Do you add voltage to it, or do you take voltage away? And that you have to find out, because all the manufacturers don't use the same. Now, to me, it's logical that you want to go to heating, you add power to that one, but some don't do that. I'm not sure why, but they don't. So you need to know whether it's normally open or normally closed. Basically, here's the normal package unit, and that reversing valve is inside this package unit. Filters. We have all kinds of different filters. This is a pre-filter. It's one of those dust stop filters you can see in residential. It just looks like a fiber mat in there. They have a 1, 2, and 4 inch MERV 4 to 8. Now, MERV is a rating how well the filter works. These are called dust stop filters. They basically stop lint. They stop some dust, but mainly lint. They're not very good filters. You can get pleated filters, and the pleated filters come in 1 to 4 inch. And the reason the pleats are preferred is because they give a whole bunch more filter area, and they'll catch much finer material, because you can see they go from 8 to 16. Cartridge filters are MERV 12 to 16, and they come from 4 to 12 inches deep. And we have bag filters. Now, bag filters can be 24 to 36 inches deep. And what they are, they're a bunch of these material bags. And as the air flows through in this direction, if it has to flow through these bags, then the material is left behind. And so these are capable of taking a lot of stuff out of the air, and they're large capacity filters. So the bag filters have been popular for a long time, and they get MERV 12 to 16, so they can be a very effective filter. Here's your MERV chart, and basically this is MERV 1 clear to MERV 20. I think it's 20, S-1. Yeah. And basically these are dust stop filters up here. These are pleated filters, and these are normally cartridge filters or bag filters. And these are HEPA filters. HEPA filters are high efficient particle filters. And these are used in clean rooms and operating theaters and places where it's really critical. And these come in, these are their efficiencies from 99.5% clear to 99.9999987. So they can be real efficient. So when you really got to have a filter, you use this last one. The difference, of course, these are very, very expensive, but they do work well. So we normally, during the COVID pandemic, we were trying to get people up into this class between 15 and 16, which will actually cut, if you look here, you can get bacteria and smoke. And if you need to remove a virus, for sure it has to be a HEPA. The only problem with a HEPA is they take a lot of pressure. They're normally 1 inch pressure just to get through them. Well, most package units don't have that much pressure. So basically you have to use one of these lesser filters that doesn't have that much pressure drop. I have done jobs where I've had to use a HEPA, and I use it as a pre-filter to the unit, and I put a separate fan on it. So basically I could use a package unit to do a small operating theater by putting a HEPA filter in a fan unit so I could take up the pressure. Dampers, you have different kinds of dampers. You have opposed blade dampers like this one. You can have parallel blade dampers like this one, and the only difference between these is this one will actually direct the airflow in a certain direction. The OBD will not. The OBD is a little bit more sure close off, but it still won't. So these can use as isolation dampers or fire dampers or dampers within the unit. So this is an isolation, this is an economizer damper section that's built into the unit. And this basically has a return fan. It draws the return air from the space, runs it through a returner damper and into the unit, into the compressor, a supply fan, and all those kind of things. And this has an economizer. So when you're in economizer mode, it means it has cold air outside. You draw in 100% outside air here, and then the return air comes in here, and this fan's job is to make sure the pressure in the room doesn't change. So if you didn't have this fan, the supply fan of the unit would have to pressurize the space to get the air in here and out this relief damper. And in the meantime, blowing the doors open. That's why we put these here, so that doesn't happen. So we have constant pressure in the unit when you go from regular mode to economizer mode. This is a different looking economizer. It's basically done on package units because they can bolt it on as an accessory. So you see the unit air comes up here, and we have an exhaust fan to relieve the air. So it can do the same thing. It can maintain the room pressure when you're in economizer mode by drawing the air out, and this fan makes up the difference. So when it's in normal mode, these are closed, the return fan's open, it puts the air into here. When you're in economizer mode, this fan is on and this is open, and the relief is open. Outside air is open, I'm sorry, that's the relief. So the outside air comes in here to the unit, and the relief goes out there. You can have face coil bypass or fan wheel bypass, heat wheel bypass, and you can have face and bypass dampers. So basically, this is a bypass damper. So this is a heat wheel. So when the heat wheel is in use, these are closed, forcing all the air through the heat wheel. When the heat wheel is not in use, these are open, bypassing the heat wheel, thus reducing the pressure in the unit, making it more efficient. Now, you can have face and bypass dampers, and that would have a damper in front of the wheel so that when it's off, no air can go through the wheel. It has to bypass. So we have face bypass dampers on coils. Sometimes we have a coil condition where we want it bypassing the coil, so you can have face. So let's talk about humidifiers. You can have humidifiers in units. There's different kinds of humidifiers. We have steam humidifiers, which is the gold standard, of course. But to do this, you have to have a steam system somewhere. So the steam comes in and is distributed in the duct with this kind of nozzle device. Or you can direct space mount them. Canister type package systems, where this is where you bring water into this canister, and you have cowl rods in here that actually heat up and boil the water to steam, and the steam is put into the duct. And the only problem with these is if you have really hard water with a lot of magnesium and calcium in them, this will plate that material out, and they don't last very long. And they're expensive, $300 to $400 a piece. So if you need that, then what you can do is you can take RO water and mix it with regular water, so you have now cleaner water, and these will last a lot longer. Now, electric steam generators are used in package units, and basically they have a canister, normally stainless steel with an open top, and it has a fill valve, and it fills this canister with water. We have a cowl rod in there that boils the water, producing steam. Or you can have the same thing with a quartz lamp. Has the same water, but instead of a cowl rod heating the water up, it's got a quartz lamp. And this quartz lamp is steaming hot, boy. It doesn't get the water warm. What it does is it flashes the surface to steam. So these also work, and these are normally used on like computer room units, things like that need humidification. The problem with these two, the cowl rod and the quartz lamp, is there's a lot of maintenance, because it does leave all those solids behind out of the water. So these are maintenance problems. Unfortunately, they are. You can also have an atomizing humidifier, which takes high pressure water and breaks it up into very small mist. Now, by high pressure, I mean 300 to 600 psi, so it's a lot of it. And the only problem with this, it should be pure water. It should be at least RO water or RODI water. And the reason is, if it has calcium and magnesium up there, not only does it break up the water, it breaks up the molecules of the calcium and magnesium, and it becomes a very, very fine powder. And in the spray, it actually paints everything white. But not only that, it's bad for your lungs. It's bad to breathe. So it needs to be pure air. They work really, really well, but in my town, we use these to cool the outdoors. Like if you have a restaurant that has a patio, they'll string these around the patio, and it drops the temperature 15, 20 degrees. They do work good if you have a hot climate. Now, pad evaporators basically go on a duct or go into a unit, and they have a canister here that's full of water, just like the other one, and we have this metal pad. It looks like a filter in it, and it wicks water up through that pad, and the air coming through it evaporates the water and humidifies the air. Now, the only condition with all these humidifiers is the air needs to be warm. Cold air will not absorb much moisture because all the moisture has been drained out of it, and so basically it needs to be in heating. Can't be in cooling. And the hotter the air, the more moisture it'll absorb. So that's kind of a deal about a package unit humidifier. AC unit controls. So normally we have thermostats on a wall that control a unit. This is a bimetal thermostat. Basically, it has a piece of metal here that changes shape with temperature, low temperature, so it can tell if it's, plus or minus 1 degree. It can close, and what happens is it reaches that temperature, it deforms and completes a circuit, thus starting a unit. We also have mercury, which mercury bulb basically have a spring coil here that changes length with temperature, and it changes the tilt of the mercury bulb. And the mercury bulb, these two wires are in this mercury bulb, so when it tilts, the mercury completes the electrical circuit. And these are actually superior to the bimetal because there's never a spark. It never has anything on the wire contacts stay clean forever because there's no air inside this bulb, just mercury. And the only reason these have fallen out of savers is because mercury is a hazardous chemical, and a lot of people worried about that. However, as a kid, I used to collect it. Do a lot of fancy things with mercury. Makes dimes shine really, really well. So anyway, nowadays we have electronic thermostats that have a circuit up here, have a thermistor telling what the temperature is. So basically, this is what we normally use nowadays. AC unit controls. Due to compressor safety requirements, all packaged AC units come with factory controls, which is a good thing. So the factory controls will control the compressor, they'll control the expansion valve, they'll watch the low pressure, watch the high pressure, watch the oil pressure, watch the temperature unit, and all those safeties are built in. We wouldn't want our control contractor to have to do all those safeties. They could be very problematic. Building DDC controls interact with package units normally by replacing the thermostat, and they attach right to the thermostat control lugs. So basically you have a red for power, you have a yellow for cooling, you have a white for heating, you have a blue normally for fan, or a green for fan. And so basically you just wire them up. Multi-stage, no problem, because they're multi-stage controls. Some units have network connections, and some of these units have their own thermostats that have a network so you can't talk to it. For those units, you have to buy a separate module that exposes the actual, points for each system in the unit. Economizers or special filters or other devices like humidifiers, unit controls may not control those. You may have to control those from an outside system. Now, really large package units, there's certain manufacturers around the country that build custom large units, and these are basically built-up panel systems with a lot of equipment on the inside of them, and these could be 40, 50,000 CFM, very large units. And instead of coming with controls and you hook your DDC controls, they will come with PLCs. And PLCs are program logic controllers, which are industrial controllers, and they work fine. They're great controllers. They're very robust, much more accurate than our temperature controls, but the problem is the owner can't deal with them. And the reason is because PLCs are programmed normally by integrators, and not, so an air conditioning factory that's doing that will not have a programmer on staff. So if you run into a problem in the field and you call him, he won't be able to help you because he hired an outside vendor to come in and program this unit. And he'll have to get that guy involved again, which is not a simple process. So every one of these I've ever installed, the owner has eventually come to me and said, we need to get rid of this PLC. So then we go in and retrofit the building controls into that unit, which means now we're controlling all that stuff inside the unit. But you can't do that. But these PLCs are problematic for owners. I understand why the manufacturer does it, but it doesn't. Okay, piping type. Most refrigerant uses copper pipe, type L, ACR type. Now, ACR is for air conditioning and refrigerant pipe, and it's special pipe. It's type L or type K. It's regular copper pipe, except it has two things. One, it's clean and capped. So it's been cleaned, has a small nitrogen purge in there, and it's capped. But there's a big difference in refrigerant piping than water piping. Water piping, the dimension is the inside dimension, ID. On refrigerant piping, the dimension is the OD, the outside diameter. So that's different. So when you're doing refrigerant, you need to buy ACR pipe. It's really important. It also comes in soft copper, so it's flexible. And this is 1/8 to 1 1/8, and that's why all these 1/8 inches, because it's OD. So soft copper is anneal copper. So basically, It's been built so it's flexible. The only problem you know how to understand is over time that flexibility disappears and it will become rigid over time. So a lot of people think they can use the flexible to make vibration isolation. You cannot. It's just designed so you can route it easily and without having to make all kinds of fittings on it. Is why it's there. It's not there as a vibration component. Can use steel pipe, ammonia system, carbon steel. No copper. You can't use copper in an ammonia system because they react. Large refrigerant systems, 6 inches above, use stainless steel tube. I've done a couple of large systems. One we had 22,000 pounds of R22 in the system, and it was all 6 and 8 inch pipes, so it was a very big pipe, and you use steel for that. Normally welded fittings, of course. And in copper pipe, in refrigerant system, we normally use silver solder, especially on liquid lines because they're under high pressure. Everything is nitrogen. All the piping comes is factory purged capped with nitrogen. And when you weld a refrigerant pipe, you have to put a nitrogen charge into the system. So you basically turn on a nitrogen tank and let it dribble through the system so there's no air in the pipe. And the reason is because air, when you weld, air will cause contaminants inside the pipe, where nitrogen will not. So we put nitrogen when we do the welding. And we have refrigeration devices. We have suction line filter dryers. And these filter dryers are designed to take out dirt, scale, and water, any moisture out of the pipe. They're on the suction lines. These have welded, sealed units. We have those. Or we have large ones that take canisters, and you can unbolt it and put a brand new filter canister in there. And these are large filter line dryers. And we have to have these on the other system because we can't have any moisture. And these are normally installed on split DX systems. So if you're actually installing a refrigerant pipe and installing a condenser, installing an evaporator, we put these in there because, we do evacuate the system when we start it up, and the evacuation is actually intended to get all the air and moisture out. But you may not get all the moisture out, and there cannot be any moisture in a refrigerator system, mainly because it's operating below freeze point, so you don't want that done. And we have sight glasses, and sight glasses are done after the condenser coil to make sure there's no air. We're trying to make sure that it's all totally absorbed, it's totally superheated, it doesn't have any bubbles in it. Sight glasses we use that way. Liquid line, entrance ports, so you can charge a system. That's what these are, like little Schrader valves put in there. Charging ports, shutoff valves. Shutoff valves in larger units are important. Mainly if you have a large unit with several coils, you'll have solenoid valves, and the unit pumps down, so when it goes off, it doesn't actually just turn the compressor off. It shuts the solenoid valve to the coil off, and the unit pumps down and goes off on pressure. The reason those are good is because when you need that coil again, the solenoid valve's open. It already has refrigerant right there to start the cooling. You don't have to wait for a compressor to get up to pressure. But shutoff valves are important if you have a large refrigerant charge. Like that unit I said I had 22,000 pounds of refrigerant. The guy that built that did not put isolation valves in it. So when we had to go work on it, we had to go get tanker trucks and bring them out and bring the charge out into the tanker trucks, work on the system, evacuate it, put the refrigerant back. It's pricey. Isolating pipe sections, and so you can actually save the refrigerant somewhere. Now, on those units, when the solenoid valve I told you about, they pump down, well, we have to have a receiver in there, and it pumps it down into the receiver. So that's where you would have a refrigerant valve, so you can pump it down the receiver, valve it off, and not have to dump much refrigerant. So now let's talk about piping. Liquid lines. There is some critical things about refrigerant piping, and the line size liquid lines are made by the mask subcooling. So we size those piping are 2 to 5 degrees. So we size those pipes on how much they're going to have subcooling of the refrigerant. Hot gas lines are sized by pressure drop and oil entrainment, just like kind of like water, but they're sized on different criteria. Suction lines, on the other hand, are sized by oil entrainment. So we got to have the oil, since we put oil in the refrigerant to oil the components, we can't let it, oil will absolutely migrate to the coldest spot in the system. So we have to have piping that doesn't allow that to happen. That's why we put risers are a concern. Risers have to be able to suck the oil up, so they have to be sized with enough velocity. A lot of times we're saying, well, let's do this real low velocity. Well, low velocity allows the oil to fall out of the refrigerant, so we have to pay attention to that. So suction risers need to be closely examined for oil entrainment and velocity. So like here's this coil. You'll notice this line looks to be one size, comes through the trap, and then it actually reduces size when it goes up. And that's to make sure the oil is entrained in that vertical rise. And then variable refrigerant flow, compressor staging, or unloading. So if you have variable refrigerant, you have to be concerned with this. Variable flow. If you have staging, you have to be concerned with this. So sometimes for staging, we use double risers. So at one condition, the oil is coming up, and at a high condition, let's say you're full flow, then what happens is the gas comes up here and won't go this direction, and part of the gas will go this direction, and will trap the oil here, and as it goes up at full capacity, it will suck the oil with it. And so that's called a dual riser. When we're at half capacity, the oil will stay here, and the first phase will go up here, and this will stay here until it gets higher capacity, and then it'll push the oil back. So that's a dual riser. Now, you don't see many of these anymore because the art of refrigeration piping has evidently eluded us. There's a lot of manufacturers that start making statements, and Trane is one of them, made a statement to me, oh, we don't use oil traps anymore. And I said, pardon? He said, no, you don't need oil traps on our systems. Well, it's not a matter of systems, it's a matter of physics. So let's talk about condensate drains. Condensate drains are really, really important for a unit because we can't allow the water to stay in the pan. If we allow the water to stay in the pan, it'll grow growies and indoor air quality issues would result. So this is, and again, condensate drains are based on physics, not on a designer's intent. I have seen many designers try to design a condensate drain that they're trying to get away from physics. You can't do it. It has to be this way. It's not my idea. This is how it has to be. So this is a negative suction deal. So if you have a draw-through unit where the cooling coil is on the suction of the fan, it'll be under negative pressure. So what we want to do is we want to keep this so this always has water in the pipe so that air isn't sucked in from the pipe or from the vent back into the unit. Now, it's not that we care about how much air gets into the unit. It is important because it's downstream of the cooling coil, but what happens if you let the air build up here, it actually causes little waves in the condensate drain, and it'll build up, and eventually it'll build a dam around this so the pan will never dry. So it's important you have this kind of coil. And what we want is we want this depth and this depth to be greater than the negative suction of the unit so that it can't suck this water out of this way. Now, a lot of times I'll see engineers say they want this cap, the vent capped, because they think it's a clean out. Well, it can be used as a clean out, but that's not its intent. Its intent is to vent this downward line. If this pipe going down fills up with water, it will now not drain. It won't drain. It'll clog this coil and no water will come out of the pan. So this has to be a vent. If you want a plug because you don't want bugs in there, it needs to be a drilled vent. It needs to have holes in it. We need air in there. It has to vent. Now you can vent it without a vent if your condensate line is big enough and it never is full flow. So normally condensate drains are third to half full, and the top part of that pipe will actually vent the trap. However, if this condensate line goes down and then turns down and goes down a wall, it'll fill. It won't be open. So that's why these traps are existing. Again, these traps are 100 years old based on physics, not design. Positive trap is the same, except now the dimensions change because we're trying to get it so it doesn't push the air pressure in the unit, which is positive now. It doesn't push the water out of the trap, and the trap becomes dry. Now it can suck air back in. It can let air in, so it'll blow that out. So we don't want that happening. So we make them that way. Now I've had contractors tell me I can't put a condensate trap in because the unit's not high enough, and it's not a good answer because the answer is then okay, you got to raise the unit up. or gotta drill a hole in the floor. We still need that trap depth. It cannot be changed because it can really cause a lot of problems if we don't do that. And here's that little dam. I guess I got ahead of myself again. Here's where if you got an inlet unit and it'll build that dam and it'll not let water out of the pan. That's a problem, and this is the condensate flowing half full, where it can actually be a vent as long as it doesn't turn down. And that's it with package unit basics. Now this video is intended to be a precursor to the package systems, which is I have 2 or 3 more videos coming one talk about specific systems of package units. But thank you for taking the course. I hope you enjoyed that. I hope you got something out of it. Thanks for being a subscriber. Have a great day. I'll catch you on the next one.